Okay, so before I start, you see, here I have written down some important constants. You must remember these facts, being an astrophysics student, right? So, mass of the sun, what is the order? 10 to the power 30 kg. Radius of the sun, 10 to the power 8 meter. Remember this, 10 to the power 30 kg, 10 to the power 8 meter. And average density of the order of 1 gram per centimeter cube for the sun. Now let's talk about our own Earth. Mass of the order of 24-25 kg. Radius of the order of 10 to the power 7 meter. And density is obviously more. It is of the order of 5 to 6 gram per centimeter cube. Okay. Now, so this is regarding sun and earth that we know of. Okay. So, what we are talking about? We are talking about star formation. Right. Now you see, the star formations start from the giant molecular clouds out there. You have seen such photographs, beautiful photographs in National Geographic channel, I think. Also on internet you can see. And maybe I will show you later on. Now the thing is that these giant molecular clouds, they have mass of the order of 10 to the power 5 solar masses. Do you understand? They are so big, large. Although remember, their density is much smaller than the average density of the sun. So this means they are extremely large. We just can't comprehend their size compared to our thinking. Okay, they are very, very large. Now, the thing is that, so this is the giant molecular cloud, mass is around 10,000, that of solar mass. Good, fine. So the next question is, what is the mass of a star? Well, it is observed that the mass of a star, we have observed stellar masses, stars with masses 0.1 to around 120 solar masses. So this is what observed. Right? Now consider this with this scenario. So what is happening? So star formation, although starts from the giant molecular cloud, whose mass is 10,000, that of solar mass, but the observed stars in our universe has so little mass compared to the giant molecular cloud. So this indicates that although if this is a giant molecular cloud, although star formation starts from there, later on something like fragmentation, that means breaking up of cloud. I am just representing this. That means fragmentation must have happened. Otherwise, you just can't explain the observed mass of the stars. So we start with the giant molecular cloud, mass 10 to the power 5 times of the solar mass, and the observed mass. So in between, somewhere this fragmentation of clouds must have happened. It must have broken down into smaller clusters, smaller parts, and these smaller parts, suppose a small part over here, this must have gravitationally collapsed and formed a star. Now this is just from observation and basic physics ideas. So now let us try to understand how we can explain fragmentation. And what we are going to do is, again, we are going to use the very basic ideas of the Jeans mass, right? We have just discussed about cloud collapse in terms of the Jeans criteria, right? So let me again rub this. So this is very important, this fragmentation diagram. Now you will understand even more. See. Right, it will be there. Some will be leftovers. Okay, so now, okay, our criteria is G's criteria. What is the G's criteria? Mass must be greater than G's mass, and I have written down the G's mass over here. Look into the structure again. G's mass structure directly proportional to temperature, inversely proportional to density. Some function is there. Now, suppose we have got a big cloud. I am not talking about the giant molecular cloud. Let us consider a very big gas cloud having mass m. And let's say that gravitational contraction has started. Okay. So, gravitational contraction has started. What does this mean? This means that the mass of this cloud must be greater than the G's mass. Okay. Otherwise, gravitational contraction can't happen. Fine. Now, as a result of contraction, what will happen?
Size and temperature and rho will increase.
See, what happens is that as a result of contraction, consider the interparticle distance. They keep on coming closer to each other. Then they will collide with each other and so on and so forth. So overall temperature will increase. Right? Now look into the expression of G's mass. Temperature if increases, G's mass increases. Again, what about the density? Density also increases. They come together. Now if density increases, G's mass decreases. So it's like this scenario, right? For temperature and density, temperature increases, G's mass increases, density increases, G's mass decreases. Now suppose as a result of this collision and coming together, suppose what will happen? Temperature increases, right? Now we have to also consider the fact that about what fact? Opacity of the medium. That means the blocking tendency of the medium. That means if the temperature increases but the cooling is not efficient, temperature increases but the cooling is not efficient, what will happen? Temperature will keep on increasing, and as a result the G's mass will change. Now we will have a new G's mass, new mj. Let us call it mj prime, right? Now again the stuff will be compared. The mass of the star will be compared with that of the new G's mass, and if it is observed that this mass is now smaller than the new G's mass. Why? Because the new G's mass value will be more because of increased temperature. Then what will happen? No collapse. Stellar collapse will stop. Okay? Okay. So this was the scenario when the cooling was inefficient. Right? Now let us consider the opposite condition. Suppose during this contraction the cooling is efficient. So what will happen? Cooling efficient means even if it contracts, the heat is being radiated out, right? So overall the temperature will drop. And if the temperature drops, look what happens. If the cloud collapses, density increases. Now because of efficient cooling, right? Let me write it down. Cloud collapses, number one. Number two, efficient cooling, right? And as a result, temperature decreases. And also you see, because of this cloud collapse, density increases. And so what will happen as a result of this? Mj will decrease. So Mj decreases. Now this is just the opposite relation. So if the cooling is efficient, Mg decreases. Any problem with that? No problem. Now let's see. I am rubbing this. Okay. So this is my big representative. victim of giant molecular cloud or whatever, cloud of mass m. So what I am saying is that Nj now decreases. Let us now consider some number. Okay, suppose this mass is around say 1000, some units, some solar mass or so. No, let me not write solar mass, some unit. Mass is 1000 and Nj becomes around 10. What will happen? It can happen that there are separate regions in the star where the value of overall cloud. Now remember what will happen as a result of this stuff, the density will not become uniform anymore. So small pockets will have more density, other pockets may have less density and so on and so forth. Now overall, because of efficient cooling, Jeans mass decreases and it can happen that some pocket may have mass more than the reduced Jeans mass, and there the cloud collapse will start individually. Okay, individually, independent of each other, because their independent mass are greater than the reduced Jeans mass, and this results in fragmentation. And this is how we can explain the observed masses of stars. So this is our fragmentation. Pretty interesting, if you ask me. Very nice concept, and a very important point is that if you don't draw this stuff, if you don't try to understand this visually, just from language it becomes really hard to understand.